All
right.
I think I'll throw a general statement.
Let's get started, everybody. All right. So I know I said my goal was to get the exam graded this weekend. That didn't happen. Busy family weekend, all that. So didn't happen. But my goal is to definitely get it done this week because I'm getting the draft reports from Capstone on Friday, and I have to turn them around on Monday. So I kind of have to get this exam graded this week so that it can free me up to do that over the weekend. So you are getting them this week one way or another. And we are getting down to the wire. We're getting down to the last bit of rebar in this class. That was really bad. That was really, really bad. That was horrible. It's Monday morning. I know. I can't make the coffee excuse because I downed my coffee this morning. Okay, let's talk about housekeeping. So I'm going to do my best to not have to use that makeup day next week, but we might have to, just depending on where we're at. I'm not of the opinion that this stuff should be rushed. I'd rather take my time with it, and if that means coming on a day that for the most part y'all are planning on being here anyways, then we'll use it. So let's talk about logistics when it comes to the grade. So exam 2 is currently being graded. Homeworks 1 through 6 are graded. Homework 7's supposed to be returned on Wednesday. My TA is working on that now. Homework 8 is due on Wednesday. So I'll open it up for questions here in a second. You all get homework 9 that Wednesday. It's due the following Friday. That's it for homework. Exam 1, 2, and 3, that's your grade in reinforced concrete design. So that should give you kind of an idea as to where things are going. Before I open it up for questions regarding homework, I do want to mention the course evals. They are open. I really would like everybody to do them. I'll give you 10 bonus points on your homework if you do them. Just like last time in instructional analysis, if you upload the picture that just says that you did it, you could run me over the coals, say I'm the worst professor ever. I just want you to do it. One thing I'll mention, I'm planning on doing a little bit of overhaul with a couple of my classes over summer. Like one of them, structural analysis. I'm really going to change some stuff in there. We're losing a week next year. We have a 15-week semester this year, and now we're going to have a 14-week semester next year, so we lose a week. So because of that, I'm planning on doing some changes, and I'd really like to hear if you all have any opinions or suggestions as to what we should do with this class. I really will take it to heart. So I really do want you to do that course eval. It'd mean a lot. Again, you get 10 bonus points. You can say I'm the worst professor ever. I just want you to do it. So if you do it, upload the picture on Blackboard that just says you did it. Bam. And can you get a homework average over 100%? Yes, you can. So, all right, sound good? Before we get into columns, you have a homework assignment on development length due on Wednesday. Floor is yours. Anybody have any questions? Have you looked at it? Okay. Any questions? This one I figure is pretty easy. I mean, it's a development length one. It's fairly plug and chug. I expect I'll get more questions in steel because the steel beam assignments did it, and that one's got a lot more going on than this one. I mean, it really is plug and chug. Everybody good? Yes.
First one, do you want us to sum the development length before doing the ratio of required steel to actual steel? Do you want us to do both the before and the after ratio, or just the after?
I think just the after, because if you can do that after, I know you can do before. So I believe that the way the problem is worded, it wants you to apply every potential reduction possible. So just give me the answer. So yeah, I mean, if you did it, I know you could just divide it out, so I'm not going to be worried about it. Yes?
So this isn't really on the homework, but in relation to the development length, I was at a lecture Friday evening, and they were talking about how stainless steel is starting to be used a little more often.
That is starting to become, it's expensive, but.
Yeah, so how would that affect the, I can't think of a name for the Greek letters, the
one that looks like a pitchfork with a sub-E.
The side.
Yeah, that
It
one.
would, and so that's a good question. So so your pitchfork constant.
Yeah.
So your psi E value would just be taken to be 1 because while it's stainless steel, it is still uncoated. See, and it's funny you mention that because a buddy of mine from grad school, she has being a professor is an awesome job, but she has probably the next most awesome job. She designs roller coasters. I mean, I know, that's pretty cool. But she actually, it's weird that you mentioned that because she emailed me about a year or so ago, and she was asking me about development length for stainless steel rebar, and asked me what my opinion on it was. And I said, well, it shouldn't be any more slippery than regular steel. I mean, maybe it's a little slippier, but it's not epoxy coated. Like if you get bare steel versus stainless steel, let's say wet, and you were to compare that to, let's say, epoxy, I don't think you see a big difference. Now, this is just my opinion, and it's not based on test data or anything like that. But unless somebody truly convinced me otherwise, I would probably say a psi value of 1 wouldn't be a big deal. Just because I don't see any significant difference in the mechanics. I just don't. If you wanted to split the difference and say, let's just use a psi value of 1.1, just what have you, I wouldn't go with 1.5. I think that's crazy. So, but I might be wrong. I mean, for all we know, there's some testing done on stainless steel rebar, and it just starts popping out like crazy, in which case, we might need to bump it up a bit. So it's a fair question. So it's funny you mention it, because I actually got that question not too long ago. So, yeah. It's good stuff. I like it. Anything else? Okay. Today, we're going to talk about columns. I'm just going to go ahead and tell you there's a lot of details coming your way. Okay? The thing with columns is not that they are conceptually difficult. They really aren't. I would argue that what is on this slide right here, if you get what's on this slide, you have got pretty much everything that there is to get associated with the concepts, the conceptual capacity of a column. So the way that we determine the capacity of a column is as follows. We determine the theoretical capacity, which is just 0.85 FC prime times the area of the concrete, which is the gross area minus the area of the steel reinforcement. So, and I think we described why last time. So if you have a column, the gross area might be, 12 by 12 if it's square, but the actual area of the concrete is that minus, the holes from the rebar. Then we add to that Fy times the area of the rebar. So it's really simple. We then compute a nominal capacity, so we take that theoretical capacity and we adjust it a bit to account for the possibility that that load is a little bit off to the side, so a little bit of accidental eccentricity, and then we reduce it further by our phi value. And that's basically it. So that is how we determine the capacity of a column. For tied columns, our phi and alpha values are a little bit smaller than our values for spiral columns. Spiral columns tend to, that reinforcement tends to confine the core of that column a little bit better. So because of that, we can bump our capacity up a little bit. And that'll become clear as we do a couple examples. And here's where I'm just going to start throwing a bunch of details at you. Okay? And that's one of the things I would say about columns is that of everything that we do in this course, they are probably the most nitpicky. There's just a lot of little things that you need to check. But I do want you to kind of understand, the reasoning. I mean, if a beam fails, that sucks. But if a column fails, that can serve to bring the whole building down. So the fact that there are these nitpicky little checks, they're there for a reason. So because column failure is scary. I mean, beam failure sucks, but column failure can bring the whole building down. So it's definitely something to keep in mind. Okay. So these are the ACI requirements for cast-in-place columns. Okay, so first off, the reinforcement ratio has to be between 1% and 8%. So our reinforcement ratio for a column is the area of the steel reinforcement divided by the gross area of the column. So remember, that's what a rho value is. It's like the percentage of how much steel you have versus how much concrete you have. But we're not looking at a beam, so our area isn't B times D. It's just the gross area of the column. A couple other requirements. So if you've got a square column, if you have a tied column, and I apologize, I'm going to use that term interchangeably. I'm going to have to watch myself, but remember, the real difference between column behavior is not whether or not they're square or circular, it's whether or not they're tied or spirally reinforced when it comes to that transverse reinforcement. If you have a tied column, so it could be a rectangular tie, it could be a circular tie, but if you have a column where the reinforcement is tied, you need at least 4 bars going up the length of that column. And if you have a spirally reinforced column, you need at least 6 bars. Okay? Now, here's another one. This one isn't a limit. This is just more of a little bit of guidance. A practical minimum column dimension is somewhere between 8 and 10 inches. So you really are never going to see a concrete column that's smaller than about like that. Okay? That's about the smallest concrete column that you're going to see, about like that. And that's pushing it. You know, most concrete columns are going to be a little bit bigger than that. I'd say a really reasonable dimension is 12 inches. That's a pretty reasonable column dimension. Here are some additional requirements for cast-in-place columns. These are for tied columns. Okay, so remember, you have a column, and you've got so here. Let me sort of draw it in 3 dimensions, just so everybody can kind of see what I'm talking about. So let's say you've got a square column that's going like this. Okay, and I'll break out some additional colors. So here's the column going up and down the length of the building. Okay. So that first requirement said you had to have at least 4 bars going up and down the length of the column, okay? But on top of that, you are also going to have some rebar tying that together, okay? So for a tied column, the tie size, the rebar that's tying everything together, if these longitudinal bars are number 10s or smaller, we can use number 3 for the ties. Anything bigger than a number 10 for the longitudinal bars, we have to go with at least a number 4 for the tie size. Okay? Now the tie spacing is the minimum tie spacing is the largest of 1 inch or whatever these longitudinal bar diameters are. The maximum tie spacing is the smallest of these 3. Don't worry, we're going to go through these limits, fairly explicitly because we have an example coming up. But the maximum tie spacing is the smallest of either 48 of your tie bar diameters, 16 of your longitudinal bar diameters, or whatever the smallest column dimension is. Because you could have a square column, you could also have a rectangular column. I'll go ahead and tell you from a practical standpoint what we're more interested in between a minimum tie spacing and a maximum tie spacing. We're really more interested in the maximum limit. Because really as an engineer, we want to use as few ties as possible. So using as few ties as possible means we need to ensure that we're meeting this maximum spacing limit. So that's really what we're going to sort of be hovering around. Okay. A couple other requirements for tied columns. So here's sort of a cross-section view. So this is if I samurai sworded or lightsabered through the length of the column, or through the middle of the column. So this is what the column will look like. This is a square tied column. And so over here on the left, this is a column with 4 longitudinal bars, and this one over here has 8 longitudinal bars. Now, if those bars are sort of hugged into the corners of these ties, you're good. However, if it's like this, and you have not only bars hugged into the corners, but you have bars within a given tie, this spacing has to be less than or equal to 6 inches. And the reason why is if that value gets any larger than that, the ties really aren't very effective in tying everything together. In fact, the rebar cage in and of itself, it doesn't really tie well together. So this dimension here and this dimension here, like between here and here and here and here, that has to be less than or equal to 6 inches. Again, that's only the case if you have longitudinal reinforcement within a tie. If it's in the corner, it's held together a little better, and that can be spaced apart, far apart as needed. Yes, sir.
And that's measured like from the outside without the bars, not from the central.
It's that clear spacing. Yes, it's that clear spacing. That's a great point. Not from center to center. Sound good? Again, I apologize. It's just one of those things with columns. It's just there's nitpicky little checks, and you just got to go through them. Now here's the thing with spiral columns. Spiral columns, the checks are a little bit easier. The spirals can't have, this is a weird limit, but it is in the spec. Spirals can't have diameters less than 3/8, so it's a number 3 bar or larger. But then again, number 3 bars, you know, that's pretty much the smallest rebar. The clear spacing between the bars has to be between 1 and 3 inches, and 2 inches is a very, very common spacing. But the reason for that spacing is going to become clear here in a second, and there's a reason why we need to go through all of the math associated with a spirally reinforced column, and I'll explain that later. First off, what I want to do is I want to get into a couple of examples. So what I've got here is example 18A. We're going to determine the axial load for this square column right here. But then let me be clear. Determining the design strength of this column is going to take about a minute, okay? Everything else, all the checks, is what's going to take the fair amount of time. We are going to go through that because I want that to be crystal clear. So we have here a square column, and then just so everybody's clear, here's a square column, and then a few slides later, we're going to have a circular column. So we'll go through and go through the process for all of it. I just want everybody to be clear on this. This isn't very difficult. Again, it can just be somewhat nitpicky. Okay, so let me get out of this. Whew, every time. Okay, so for this column, I believe, hold on. Okay, yeah, 4 KSI concrete, 60 KSI steel. Okay. This is a really, really straightforward problem. Okay, so here's the column. Let's see if we can find a couple basic parameters. First off, what is the gross area of this column? All right, this should be pretty simple. Yeah, and it's just b squared. 16 times 16. So 256 square inches. Okay. Now we have the area of the steel reinforcement. That's provided. That's 8 square inches. Okay. So the 8 square inches, just so everybody's clear on the dimensions, that comes from 1, 2, 3, 4, 5, 6, 7, 8 bars, 8 number 9 bars, and those 8 number 9 bars are coming in and out of the screen. Okay, so that's these 8 bars here. Meanwhile, we also have these longitudinal ties, or these transverse ties, they're number 3 size bars, and they're spaced at 16 inches. So in and out of the screen, every 16 inches, we've got one of these transverse ties. So we're going to have to check limits on that as well. The only other thing I'd like to ask is, what is phi and alpha for this column going to be?
.65 and 0.8.
0.65 and 0.8. Everybody okay with that? And again, that's just straight out of the spec. It's in your textbook. It's pretty straightforward to find. Okay, so once you've got that, the capacity is pretty straightforward. Just 0.85 FC prime times the area of the concrete plus Fy times the area of the steel. And so, plug and chug, this is going to get kind of long. They got an answer for me?
I got 688.
688.1. Do I have a second on that? 688.1. What are the units? Kips. So that's the, if you want to know what the axial strength of that column is, that's it. In other words, here's the column. I'm taking the column and I'm pushing on it with some factored load, and as long as that load is less than 688.1, I'm good. That's it. Bless you. Now there's, obviously we have a dead load, a live load, and we would factor that to get this, compare that to that, and that's it. I wish I could make the problem any more complicated, but I really can't. That's about it. Now, however, there are oodles of detailing checks we're going to have to do. So let's just get through those one at a time. Okay? So let's take that one at a time. So, if you ever hear structural engineers refer to the term detailing, this is sort of what they mean, which is checking all the nitpicky little limits and things. And they seem nitpicky, but usually they all have a very explicit, real reason why you're doing it. So, it's like, for instance, for those of you in steel design, like it might have seemed a little nitpicky to check bolt spacing, but there are reasons why. If the bolts got too close together, you couldn't put a wrench around it. If they got too far apart, you get water between the connections. So there's reasons for these checks. Okay, so the first one we're going to look is at steel percentage. And we can get away from me. Steel percentage. So that's our reinforcement ratio. Hey, got that backwards. AST over AG. So this is 8 over 256. So as a number, 0.31. Do I have a second on that?
Yep.
And so that has to lie between 1% and 8%. So we're good. So therefore, this is okay. And so I'm going to say it's okay, and then I'm going to write on here between 0.41 and 0.08. That way, when I write okay, like I write that the limit's good, you don't go back to your notes and go, well, why? Now you know why. Because it's between 0.01 and 0.08. Okay. Next one, let's look at the number of bars.
Is it less than that?
That's
Yeah.
Wait.
That's OO.
Oh, you got an extra 0.
You're right. Did I do something wrong?
Yes.
What's wrong?
You do it, yeah.
So
0.03.
So see, you say I did something wrong, but I put the number down and somebody seconded it, so.
And he seconded Nathan.
Oh, okay, so I don't matter, no. Okay, the number of bars. How many longitudinal bars are we using along this column? 8, right? Now, why am I remarking about that?
Or at least 4.
We have to have at least how many bars for a tied column? 4. So that is a check that you need to perform. So that's okay. I'm going to put okay because it's greater than or equal to 4. Okay? The next one is the minimum tie size. Okay? We are using a number 3 tie. Okay? And what I'm going to say is that's okay is because number 3 ties for longitudinal bars that are number 10 or small, right? Because if you have a longitudinal bar that's a number 10 or smaller, your ties have to be at least number 3s. Am I right on that? Yes.
So this is more of just a conceptual thing, like visualizing it. So like when a beam fails, obviously if you put too much weight on it, it bends down, it cracks, or the opposite way. How would this fail with the ties and?
That's a great question. That's a great question. And I am not an artist, so I'm going to let my next slide do it for me. But what's really going to happen is that. Okay? So you're going to load it in compression, and basically it's just going to crush. Okay? You're going to start to, the first thing that you'll see is that concrete that's around the ties, that's on the outside, will start to crack and fall off. If you've ever heard the term spalling, maybe you've heard that term spalling. So that's what spalling is when that surface concrete starts to crack and fall off, that's spallation. Then what you'll find is that these longitudinal bars will start to buckle, the inside will start to crack, and then it's gone. Okay? Now, the thing is, spirally reinforced columns tend to operate better because they confine that core a little bit. Okay? The upside is you get to use a stronger, you get to use higher phi values and higher alpha values. The downside is that you got to provide a boatload of spiral reinforcement. And so we'll get to that here in a second. But how does it fail? That's how it fails. That's a whole lot better than anything I could draw on the board. That's pushing the point. So. And I had students a couple semesters ago remark about my handwriting. It hurt my feelings. Yeah, let's see how it is. I'm kidding. Not really. All right, so now let's look at tie spacing. Okay, now we have minimum tie spacing. We have maximum tie spacing. Okay, so let's look at the minimum. Okay, what is the minimum tie spacing limit for reinforced concrete column? Somebody tell me. Oh, what's it say?
Largest 1 inch or 1 long.
Okay, it says the largest of 1 inch or 1 longitudinal bar diameter. Now, what is that going to be for this column? Now you did it again. You did it again. The area, bless you, the area of a number 9 bar is 1 inch. What is the diameter of a number 9 bar? There we go. No. There we go, the 1.128. Remember, a number 9 doesn't work that way. The number 9 has the area of 1 square inch. So S min is the maximum of 1 inch or that bar diameter, which in this case is the maximum of 1 inch or 1.128. So 1.128. Okay? Now, maximum tie spacing is what? There's 3 quantities we got to check, right? What are those 3 quantities? Somebody tell me one of them.
48.
There we go. So let's put that over here. 48 tie bar diameters. So that's 48. And what are the tie bars?
Number 3.
And now what's the diameter of number 3? There we go. Yeah, you can use 3/8 on number 3. Okay, and so what does that come out to be? 48 and 3/8, so the 8's, okay, 6, 18 inches. Did I do that right?
Yep.
Okay. So that's one of them. And then what's the next one?
16 longitudinal bar diameters.
So that's 16 times what? There we go. Okay, and so that comes out to be what does that come, actually, what does that come out to be? 18.05. And what about the third one? It's the least
Lateral column dimension.
So what that means is that if you had a column that was rectangular, so here's the column, it would be this dimension. But we have a square column, so it doesn't really matter which one we use. And what is that going to be? 16 inches. So of these, S max is what? 16 inches. Now what is our actual tie space?
16 inches.
There we go. So S max is 16 inches and S is 16 inches. Okay. Okay. Does that make sense? And it's okay that it equals max. And again, from a design perspective, what I usually do is whatever S max is, that's just what I use. That just means, you know, the larger tie spacing means the fewer number of ties. Less stuff to tie together in the field. Oh, sorry. Yes, sir.
How are these tied in the field? Do we zip tie, or are we just using string? I mean,
There's a, hold on.
it's probably like a metal wire or something.
It's a little metal wire, so rebar ties. So usually what you'll find is folks have this little like handle that looks like that, and it's got this weird little hook on it. And rebar ties are just these little spools of wire, and so they'll have the two pieces of rebar that they need to tie together, wrap that, stick the handle in, you know. Now there's a,
That can get super tedious.
well, it can, yeah. There is a, like a cool little rebar tying gun that you can use. I don't care about grammar. Actually, I do like grammar, but I don't care about right now. Okay. I don't care. This is actually kind of cool. So, let me go back here. You see that?
Oh, dang.
That is kind of cool. So, hold on. I don't care what it means. I want to see it. See what it's doing? See how it like feeds it, it spools it, and then cuts it? Yeah. So that's another way that it's done, but it's one of those two. The material, the medium, is usually a wire, like a little
Now,
small gauge wire.
there wouldn't need to be any thought into like what the wire would be, right? Because when it's surrounded by all the concrete, it wouldn't matter.
It's just to hold it together while, yeah. So that's a fair question. The short answer is no, it doesn't really matter. All right, sound good? Okay, the last thing that we need to check is this clear bar spacing. Now, first off, let me ask you a question. What was the space, what was the maximum space that we could have between those clear bars? Anybody remember? It was 6 inches, right? Now, here's the big question I want you to understand. Is that limit even applicable for this column? Yes or no? Yes, right? So, here's what I'm getting at. So this is the limit that we're looking at. Remember, we don't check that limit when we don't have pieces of rebar within a given flat portion of the top. So if all we had was reinforcement like this, and we just had 4 longitudinal bars, we wouldn't need to worry about it. However, that's not the case. Our column looks like this, right? And so we need to ensure that this clear dimension between here and here is less than or equal to 6 inches, okay? So the first question I want you all to be able to answer is when you are supposed to check this limit. And on a problem like this, yes, you are supposed to check it, okay? Does that make sense? Are you okay with that? Okay. Now, how do we check it? Okay, I'm gonna put some thought into this because I really want this to make sense. All right, I'm gonna copy this down here. Okay. Let's take a look at this this bar spacing. I want to show you how I'm going to compute it. I'm going to start off with 16 inches. Okay. Then what I'm going to do is I'm going to subtract off 2 times 1.5. Okay. So here's the column, and so I'm going to start off by subtracting this distance here and that distance there. Then the next thing I'm going to subtract is 2 times 3/8 of an inch. Why am I subtracting 2 times 3/8? Because that's my tie bar diameter there and there. Everybody with me so far? So if I were to stop right now, what would that give me? That would give me the clear distance between here and here, right? Everybody with me on that? Okay. Now, the next thing I'm going to subtract is I'm going to subtract 3 1.128. Okay? So in other words, I'm subtracting 3 of these. Actually, let me do that here. 1, 2, 3. Now, if I wanted the clear spacing between those bars, what do I divide that by? 2. Now, let me ask you this. Before I hit plug and chug on this, what if instead of 1, 2, 3 bars, what if I had 1, 2, 3, 4 bars? How would this calculation change? This would be a 4, and I would divide the whole thing by what? 3. Does that make sense? Okay. So, multiply that times 3, divide that by 2, what do we get? Is that okay?
Yes.
Why? So the value's okay. That's seconded. You were seconded.
I was second.
Okay. Now is the value okay?
Yes.
Now were you seconding him or me?
I'm second.
Oh, okay.
Someone's always
All right. Sound good? I know there's a lot of nitpicky checks, but they're not hard, are they? That's it. So, yes.
So, are there gonna be some problems where this isn't square or one?
Possible.
Alright, so we'll have to check it twice.
You're right, yeah. But maybe you'll have to check it twice. For instance, what if here's your column and your reinforcement is like this? Do you have to check it twice? You're only going to check this side. You don't need to check this side because it's hugged in a corner. The only reason that you would need to check this side is if you had a bar there. You see what I mean? And how would you, what would deviate or what would be different? You'd multiply or you'd subtract 5 bars, but you divide by 4 spaces. Okay? Does that make sense? That's square columns or rectangular columns. So. And if you're wondering where rectangular columns can show up, I mean, architectural considerations can require rectangular columns. Also, if you have a direction of the building that is susceptible to wind load or seismic load, you might want to make the column deeper in one direction than you do in another. So.
Does this also apply for like concrete bridge pier columns?
Yeah, pretty much. The only thing that's different is your fee values can change and some of your stress calculations can change because the limit states are a little different. But the concepts are the same. It's not as if concrete, see, here's the thing, a steel beam doesn't really care whether it's in a bridge or a building, just like a concrete column doesn't really care whether or not it's in a bridge or a building. It's still going to behave the same way it's going to behave. The little nitpicky stuff can change here and there, and some of the stress checks can change here and there, but in the end, the behavior's the same. So, it's a good question. The only other thing that can get a little different, this is probably a bigger deal in bridges than it is in buildings, is if you have a really, really tall pier, you might have to consider buckling. So, and I'd argue that can sometimes be a little bit more of an issue in bridges, because in some instances you have some really tall bridge piers, so that's just the nature of these. Any other questions? Okay. So let's talk about spiral columns. So the reason why we use spiral columns is because spiral columns, they tend to confine the core of the column a little bit better. So in a rectangular column, or a tied column I should say, again, I won't use that interchangeably, but in a tied column, what happens is the exterior concrete spalls, and because those tie bars really aren't doing a very good job at confining the core of that column, the longitudinal bars buckle, the inside crushes, and then that column's done for. Whereas for a spirally reinforced column, it's a little bit different. See, what's happening is you're taking this column and you're loading it in compression. Have you ever, I'm trying to think of the best example. Have you ever had like one of those like plastic syringes, your ones that didn't have a needle on it, obviously, and you put your finger on the end of it and you like press the plunger, and you know how it's kind of tough to do that? Because you're pressing the plunger. What is the plunger doing? Well, the plunger's applying a compressive load, but what's the syringe doing? The syringe is almost kind of acting like a balloon, right? And so you press it, it's sort of holding everything together, right? You know what I'm talking about? Well, honestly, that spiral reinforcement kind of acts like that. Really what's going on, and this is going to break it back to Engineering 216, but this is a pressure vessel. Did y'all do pressure vessels in 216? Yes, you did. I know you did pressure vessels with me because I know it was in my notes. I taught the class. I promise that you did it in fluids? Why'd you say fluids?
Just getting prepared for the exam.
Oh, you're a funny guy. Smart guy. All right, so essentially what's happening with spiral reinforcement is that spiral reinforcement is sort of acting like a pressure vessel. One of the topics that you do in 216, and if it's been a while since you've had the class, I know that you did it, it's been a while, I know that you probably remember that whole Moore circle thing. I mean, you can't do 216 without at least seeing Moore circle once. I don't need to do that. I know you've seen it. But Moore circle is an expression or a reflection of multiple stresses happening all at once. And then what you do is you start looking at, well, what are some applications? What are some instances where you actually see multiple stresses acting all at once? Well, beams are an example of that because in a beam you have bending and shear, and a pressure vessel is the same as well. Like imagine if you have a balloon and you blow up a balloon, that balloon just stretches, right? It just completely expands. So any one element of the balloon, the rubber in the balloon, is seeing stress this way and this way. Well, a pressure vessel is sort of just like a metal balloon. And so is this rebar that's confining the core of this column. And so what you do to size that spiral reinforcement is you say, okay, I'm going to try and size that spiral reinforcement so it can contain the full capacity of the core. Well, what's the capacity of this internal core of the column? Well, it's 0.85 FC prime times the area, which is the gross area minus the area of that central core. And we say, well, okay, what's the strength of the spiral? Well, the strength of the spiral, that comes from pressure vessels from Engineering 216. And so basically all we're doing is we're saying 2 times the area, because we're cutting a section, times the yield strength, times whatever that percentage of reinforcement is. So that's that percentage of spiral steel, that's the reinforcement ratio. So we set those two equal to one another and we solve. And so theoretically it comes out to 0.425 times this algebraic expression here, but the spec says, close enough for government work, let's just round that up a bit. So we round that up a bit and we say this is the amount of reinforcement required in order to effectively contain the core of that column. Now, the only other thing that's maybe a little confusing is how exactly do you compute rho? I mean, rho for the longitudinal bars was the area of the steel divided by the area of the concrete. Well, how do you do that for bars that are going this way, that are spiraling up a column? Well, the way that we do that is so those bars are sort of going like this up the column. And so the way that we do that is instead of taking area of steel divided by the area of the concrete, we take the volume of the steel divided by the volume of the concrete. And so how do we compute volume? Well, we take the spiral and we say, well, how much steel is in a single revolution? How much steel goes through a single revolution? Well, I propose that the amount of steel that goes through that single revolution is the area times the circumference. Because basically, if I were to look up and down, I'd have a piece of steel like this, and it goes around like that. So I take the area of that spiral times pi times the circumference. Pi times the diameter, which is the circumference. So the area times that length will give me the volume. And so what's that diameter? Well, it's the diameter of the core minus a bar diameter, because I got to come in half a bar diameter and half a bar diameter on either end. So that's how I'm getting this volume of the spiral right here. It's just the area of the bar times one circumference, times one length. Okay. As for the volume, well, I'm talking about the volume across a single pitch. So how do you determine the volume of a cylinder? Does anybody remember how to do that? You take pi d squared over 4 times the height. Remember that? So in this case, the height is the spacing. Across one pitch is that spacing, and the diameter is just the diameter of that core. So we take the volume of the spiral divided by the volume of the concrete, and we just do a little bit of algebra to rearrange, and we get this. So the long and short of it is, what's inside that box right there, that is the actual percentage of spiral reinforcement that we are providing, and that's the limit. Okay? We have to at least meet that. So as long as the amount that we're providing is less than or equal, or is greater than or equal to what we actually need here, we're good. Okay, does that sound good? So, less details on spirally reinforced columns. This will go quick. So what we're going to do next time is this. Next time, we've got an example that we're going to look at where we compute the capacity of a circular spirally reinforced column. And then the next thing that we're going to do is look at column design. And it's really, really easy to design a column. We're going to design, don't worry, we're going to design a square column. We're going to design a spiral column. And then we will begin the last topic of the semester, which is interaction. Okay? We'll see where we get, but we are making real good progress. So this is, I'm really happy with our pace. Sound good? Steel's up in 10 minutes. That's all I got.